Welcome back. This session we can concentrate on classroom workbook. Okay. Write down problem number 1. Let me read out. For the circuit shown, assume that the NMOS transistor is in saturation. Its threshold voltage is 1 volt. Its transconductance parameter mu and C ox W by L into. You may say that why it is called transconductance parameter, because we are familiar with transconductance GM, but it is transconductance parameter of your device. Don't confuse. Okay. Transconductance parameter mu and C ox W by L is equal to 1 milliampere per volt square. Neglect channel length modulation. Lambda is equal to 0. And body bias effect. There is something called body effect or bulk effect, saying that you can neglect all higher order effects. Under these conditions, the drain current ID in milliampere is, okay. Let me just write the information given, which is given. Problem number 1. VT is given. VT is equal to 1 volt. And transconductance parameter mu n C ox W by L is also given, which is 1 milliampere per volt square. Neglect channel length modulation, and then asking for ID. What is ID? Circuit is given. Circuit is VDD is equal to 8 volt, and this is 1 kilo ohm, 1 kilo ohm, R1 3 mega ohm, R2 5 mega ohm, and this is ID. This is RD and RS. Okay, this is GATE 2017. GATE 2017 for 2 marks. Okay. Now, what are maybe the problem, right? Just listen. I already told the procedure, but the same procedure. Any circuit, whether it is BJT or MOSFET, right? Let us say circuit is given in the examination. Okay, I'm just giving you the procedure. If circuit is given, classify the problem into AC analysis or DC analysis. Okay, classify the problem into either AC analysis problem or DC analysis problem. How do you know? Based on the problem statement, asking for voltage gain, current gain, input impedance, output impedance, etc. Surely that is related to AC analysis. Asking for capital ID, capital VGS, right, and region of the transistor, resistor value, all those things are related to DC analysis. Okay. Therefore, if you classify the problem into, then immediately find AC circuit. After finding the AC circuit, immediately find the configuration. Find the configuration. Then go for or apply formula. apply formulae what we studied or derived. Now, if the problem is related to DC analysis, then get a DC circuit. How to get DC circuit? All AC signals to be taken out, and for a DC capacitor acts as an open circuit, for a DC inductor acts as a short circuit, right? We have to take DC equivalent representation, okay? DC circuit, then apply KVL equations, either at input KVL, either at input or output. Sometimes we need to apply both. Then solve the equations. Solve the equations along with devise equations, along with devise DC equation. Devise DC equation. What is devise DC equation? If you consider, let us say BJT. If you take BJT, what is devise equation? IC is equal to beta into IB plus 1 plus beta into IC naught. That is what is your BJT DC equation. Okay. Now, if you take JFET, but we don't have JFET in syllabus, therefore, let me give you directly MOSFET. Therefore, if you take MOSFET, right, what is ID? ID is equal to mu n Cox W by 2L into VGS minus VT whole square, provided transistor is in saturation. Therefore, this is true only when it is in saturation. For example, therefore here this is true only when the transistor is in active region. Therefore, this is for active region. Remember, in the case of BJT, when I say active region, the parallel region or the equivalent region in the case of MOSFET is saturation region. Okay. Here this is what is current control current source, but here this is voltage controlled current source. But we have another ID, but we don't have IC, which is what is IC sat basically, but here we have ID linear. This is what is called ID linear, which I already told before, mu n Cox W by L into VGS minus VT into VDS, right? This is when transistor is in linear region. That is true when transistor is in linear region. Okay. Therefore, this is saturation. But here, this is what is voltage controlled resistor. Voltage controlled resistor. Okay. When I say this is what is active region, right, and that is saturation region. Here, saturation region is nothing but linear region or active region in the case of MOSFET. I already told these points, right? That is what we need to use. Only when the transistor is in, only when the MOSFET is in saturation, remember we have to use this equation. Only when the BJT is in active region, we have to use this equation. And I gave you the condition to check whether transistor is in active region or not. Similarly, I gave you the condition to check whether the transistor is in saturation region or not. Okay? Those are all important. Blindly you can go ahead, like sometimes assuming MOSFET is in saturation and then taking ID is equal to mu n Cox W by 2L into VGS minus VT whole square. But sometimes it needs the region also, then we have to use the proper current equation. Okay? This is what is the procedure which is common for both BJT as well as MOSFET. There is no change. Take the procedure. Therefore, this is the procedure. Then try to apply the procedure to solve the problem. Tell me, based on the problem statement, is it DC analysis problem or AC analysis problem? Surely that is DC analysis problem, because asking for ID. If the problem is related to DC analysis problem, DC circuit. Actually the circuit itself is DC circuit. No AC signal, no capacitor, no inductor. And apply the KVL equations. We need to apply the KVL equations along with the device equation. And he told that transistor is in saturation. Then we have to use this equation. ID is equal to mu n C ox W2L into Vgs minus Vt whole square along with KVL equations, right? Input KVL or whatever it may be to find your ID, then problem is over. Okay? Blind procedure follow. Okay? But when I say DC circuit, the DC circuit can be anything related to DC quantities. Okay? Not only always self-bias circuit. Okay? There are some other bias circuits under they will come under DC circuit, like current mirror, whatever we had seen in the case of BJT, which we did not see in the case of DC analysis, right? But current mirror also will come under DC circuit only. Am I getting this? Okay. I'll give you 30 more seconds to write this, then try to solve the problem. Okay? Done? Okay. Now let's solve this problem. Now this is what is our DC circuit. To apply input KVL, right? We need to write like V Thevenin, R Thevenin. But I told no need to calculate R Thevenin because the current entering into gate of your MOSFET is 0. Then the drop across that R Thevenin is equal to 0. Okay. If I write, okay, if I equivalently represent this, apply V Thevenin because I'm going to apply Thevenin's theorem for this portion. Therefore, then what you get, this is nothing but V Thevenin, R Thevenin, then the circuit is becoming, this is VDD 8 volt and this is 1 kilo ohm and this is 1 kilo ohm. Now this is ID and this is what is V Thevenin. This is R Thevenin. Right? No need to calculate that. What is V Thevenin? V Thevenin is equal to voltage divider network R2 divided by R1 plus R2 into VDD. Therefore, what is that? R2 is nothing but 5 mega ohm. 5 mega divided by 5 mega plus 3 mega, 8 mega into 8 volt. 8 will be cancelled, then it is 5 volt. Therefore, what is V Thevenin? 5 volt. Therefore, what do you mean by V Thevenin? This is what is the voltage. Now, try to apply input KVL, right? Then you will get it. Can I erase this? Okay. Now apply input KVL. Input KVL. V Thevenin is equal to, the drop across R Thevenin is 0 because there is no current. Then VGS because this is gate, this is source, this is nothing but your VGS, gate to source voltage. Okay, VGS plus the drop across 1K. What is the current which is flowing through? This is drain, right? This is drain. Therefore, what is the drop across 1K? The same current, the current which is entering into drain, same current is coming out of source. Therefore, ID into 1K. ID into 1K. Our aim is to find ID only, right? Therefore, you know VThevenin 5 is equal to VGS is not known to you, VGS plus ID into 1K. This is what is our equation 1. And we know, don't apply output KVL. If you apply output KVL, you should know VDS. We don't know what is VDS, right? Therefore, again, you'll get one more variable. Already we have two variables, you'll get one more variable, which we don't want, right? Therefore, already we know the relation between ID to VGS. That is what your device equation, right? Therefore, what is saturation current equation? Saturation current equation, saturation ID. Therefore, ID is equal to mu n Cox W by 2L into VGS minus VT whole square, right? Therefore, now mu n Cox W by L is already given. What is that? 1 milliampere, and VT is already given. Therefore, this is nothing but 1 milli by 2 into VGS minus 1 whole square. Therefore, now you have two equations, two unknowns, then try to solve, you will get the answer. Then you may say that directly let's substitute VGS with respect to ID and solve the equation, you will get the answer, right? But remember, it's better to solve VGS first. If you have multiple solutions, then it will tell you the answer. Okay? Try to do it. Therefore, this is what your ID. Okay, what I do, therefore this is what is equation 2. Then what is ID in terms of VGS? 1 implies 5 minus ID is equal to 5 minus VGS divided by 1 kilo. You substitute that in equation 2, therefore 2 implies 5 minus VGS divided by 1K is equal to 1 milli by 2 into VGS minus 1 whole square, right? Therefore, tell me that 1K, if it is going to right hand side, 1K into 1 milli, that will be cancelled, the 2 will go here. Therefore, 10 minus 2 VGS is equal to A square, VGS square plus B square 1 minus 2AB minus 2 VGS. Then if you take this, you will get VGS square minus 2 VGS, and then it will become plus 2 VGS. Cancelled, then plus 1, then it will become what? Minus 9 is equal to 0. Therefore, what is VGS square? You will get VGS square is equal to 9. Then what is your VGS? VGS is equal to plus or minus 3. Then which one you take? Plus 3 volt or minus 3 volt? Remember, because this is NMOS, always for NMOS we take VGS positive. Therefore, when I say VGS positive, therefore VGS is 3 volt for NMOS. For NMOS. Now you substitute that VGS 3 volt, then you will get 1. Therefore, 1 implies 5 is equal to 3 plus ID into 1K. Therefore, ID is equal to 2 divided by 1K, which is 2 milliampere. That is fill in the blank, okay? ID is equal to 2 milliampere. Everybody understood the procedure? Procedure is very important. DC circuit, very simple, just KVL equations along with the device equation, But remember, the device equation we have to take properly. If the transistor is in saturation, we have to take saturation current equation. If transistor is in linear region, we have to take linear current equation. If transistor is in a cutoff, ID is equal to 0. Okay, there is no special equation for that, neglecting subthreshold region. Okay, fine, take it. See, ultimately answer is important, but to get that answer, procedure is very important. Over? Okay. Now, problem number 2. Kind of theoretical problem. Problem number 2. For N channel enhancement type mode MOSFET is biased at VGS greater than VTH and VDS greater than VGS minus VT. Okay, where VGS is gate to source voltage, VDS is drain to source voltage, and VTH is threshold voltage. Considering channel length modulation effect to be significant, the MOSFET behaves as, tell me. Option A, voltage source with zero output resistance, voltage source with non-zero output resistance, current source with finite output impedance, current source with infinite output impedance. Okay, see, I already told, right? Problem number 2, given VGS greater than VTH, okay, and VDS greater than VGS minus VTH. This is what is given, right? Right, and lambda, channel length modulation is there. Therefore, channel length modulation is present. Right? Then, you remember I told you, right? Point number 1, if VGS is less than VTH, what I told, this is nothing but cutoff. I am just repeating once again. When I say cutoff, your MOSFET is nothing but what? Your MOSFET is open circuit, right? This is drain, source, gate. Between drain and source, it is open. And your ID is equal to 0. Therefore, what is your ID? ID, actually there is a reverse saturation current through the channel that you can take approximately 0 for all VDS. Whatever VDS you apply, your ID is equal to 0. Case 2, right? When VGS greater than or equal to VTH, now channel is formed. Therefore, between drain and source there is a channel. Then you apply VDS, you get the current. But now that depends on, let us say, if VGS is, VDS. See, I am repeating the same thing again and again. What is the reason? You will remember it. With respect to problem, we will remember. Therefore, whatever VDS you have, the VDS, if that is less than VGS minus VTH, then I told that your MOSFET, whatever MOSFET, right, between drain, source, gate, it will be a resistor, variable resistor between drain and source, and the resistance value is controlled by gate to source voltage, right? Therefore, this is nothing but an ID is equal to mu n Cox W by L into VGS minus VT into VDS. This is what is linear current equation, because this is what is in linear region. Now, if you consider the other one, which is nothing but if VDS is greater than or equal to VGS minus VTH, then what is your MOSFET? Then your MOSFET is nothing but what? Is nothing but a current source. That's what I told, right? It is nothing but a current source, but the current source value is controlled by gate to source voltage. Then in this case, I told you what is ID? ID is equal to mu n Cox W by 2L. Don't forget 2, okay? W by 2L into VGS minus VT whole square. But I told you, right, this is nothing but ideal model. If you consider practical model, what is practical model? Practical current source. Practical model is nothing but practical current source. Okay. Similarly, this is what is practical model. If you take ideal model, that is nothing but short circuit. Okay. And this is what is practical model. Maybe that is what I told that time, right? If you go back and then see, tell me what is the answer now? Answer is, he has given VGS greater than VT, there is a channel formation, and VDS is greater than VGS minus VT. Therefore, the transistor is in saturation and channel length modulation is present. Then practical voltage source, practical current source. Therefore, it is a current source with a resistance. That is the answer. Just to add, because everything we have taken practically, therefore we will have some resistance here. This is what is representing your channel length modulation, right? Whatever we are having, which is nothing but your small RD. That's what people represent. Therefore, 1 plus lambda into VDS. Because now channel length modulation is there. This is what is your saturation region. Practical model, including channel length modulation. Therefore, practical models are level 2 models. Because in the problem statement saying the channel length modulation is equal to channel length modulation is present. See, if channel length modulation is not there, this is simply, instead of practical current source, it will be ideal current source, but the current will be controlled by gate to source voltage. Then if I say ideal, this is short circuit. If you ask me the answer is C. Current source with finite output impedance. Current source with finite output impedance. It's not infinity. If channel length modulation is not there, then that is infinity. Okay. Over? Okay. Now write down problem number 3. In the MOSFET amplifier of the figure is the signal output V1 and V2 obey the relationship. Asking for what is V1 and V2 means the relationship between V1 and V2. Okay. Problem number 3. Okay, circuit is given RD by 2. Okay. Circuit is this is VI, this is RD by 2, RD, now this is V1, this is V2. Now asking for the relationship between V1 and V2, right? V1 and V2, okay. Now, given some arrow, what does it mean? It is connected to some supply, that is what is VDD, okay. This is what is connected to ground. Now tell me, actually we did it, you remember, drain, source, gate, right? What is this? You remember we took some general circuit and then we calculated V01 by VI, V02 divided by VI, that's it. If you know V01 by VI, V02 divided by VI, you take the relation or ratio, you'll get the answer, right? Now to get the relationship between V1 and V2, for that first of all what is V1? Therefore what is V1? We know that, right? What is V1? V1 is equal to minus mu into RD divided by capital RD plus small rd plus 1 plus mu into rs, right? If you follow like this, right, then you'll get V2. What is V2? Mu into rs divided by capital RD plus small rd plus 1 plus mu into rs, right? You'll get the answer. Try to do it, okay? Then what is this? What is RD? RD. But what is RS? You keep it like this. Okay. Let me try. Let me take this as RS only. This is your RS. Okay. Now what is V2? Into VI. Similarly, what is V2? V2 is equal to mu into RS divided by capital RD plus small RD plus 1 plus mu into RS. If you take the ratio, the denominator will be cancelled. Therefore, V1 by V2 into VI, right? V1 by V2 is equal to this, and this will be cancelled. Mu will be cancelled. VI will be cancelled. Minus RD divided by RS. But what is RS? RS is nothing but RD by 2. Therefore, minus RD divided by RD by 2. Then it will become minus 2. Therefore, what is V1 by V2? Minus 2. What is the answer? D. Therefore, V1 is equal to minus 2 into V2. Answer is D. Problem number 4. After this, I'll give you time to write. Then after this, problem number 4. We remember we already solved this, right? We have to take small signal V1, small signal V2, because input is AC voltage. Even though in the problem statement capital V1, capital V2, it is not capital V1, capital V2, kind of we need to take what? The AC signals for your, because input is AC signal. Strictly speaking, it is small V1, small V2. But in the problem statement, this according to our notation, capital letters we use for DC and small letters we use for AC. Sometimes capital letter subscript small, which is nothing but DC plus AC. Okay, that's fine. But these are all AC. If you ask me just to have the correction, even the problem is having capital V1 and all, for with respect to our notation, small V1 and small V2, then small V1 divided by small V2. Therefore, small V1 divided by small V2. Because this is small Vi. Problem number 4. Two identical NMOS transistors M1 and M2 are connected as shown below. P bias is chosen so that both the transistors are in saturation. Therefore, saying that both are in saturation. The equivalent GM of the pair is defined to be dou out by dou Vi at constant V out. The equivalent GM of the pair is problem number 4. Circuit is this is defined with V bias, which is fixed voltage, and this is nothing but what? This is what is Vi and this is V out. This is V out and this is Vi. And this is what is I out. And this is M1, this is M2. Then asking what is GM of this transistor, okay? The equivalent GM of the pair. Therefore, this is what is the pair, okay? Now, if you treat, can I treat this as a black box? I don't know what is there inside, but simply it is defined with input voltage Vi and defined with output voltage V out, and the current which is entering into block. Then what is GM? It can be anything, any circuit, okay? It can be any circuit or any system. Then what is GM? GM is defined to be what is the change in output current? What is the change in the output current? The change in output divided by due to change in input when Vout is constant. That is the definition. See, this is true not only for a device, this is true for a system, or this is true for a circuit also. Therefore, that is what is going to give you the transconductance parameter of your circuit. Okay? Therefore, GM is defined as for a given change or for a small change in input voltage, what is the change in the output current? Not because of output voltage, therefore keeping output voltage constant. Therefore, GM is defined as what is change in output current because of changing input voltage only. That's why Vout is constant. That is fine. Now is asking, this is the definition, that is what is given, asking for this. Now if I treat it, therefore I can say one thing. Therefore what is this? This is nothing but, right, what is GM of this? This is GM1, this is GM2. Saying GM1 plus GM2 or GM1 minus GM2 or GM1 by GM2 or simply something GM by G0 or GM something. Okay, that is what is saying, some different options. I can say one thing, in series current is constant. Whatever current which is what is flowing through M2, the same current is flowing through M1. Therefore, can I say this is nothing but current ID1 divided by change in input voltage. Okay, when Vout is constant. What is Vout? Vout is equal to VDS2 plus VDS1. Let us say Vout is constant, then VDS2 is constant, and then VDS1 is also constant. Therefore, let us say VDS1 is constant. Therefore, instead of VI, can I call this as VGS1? VGS1. Therefore, in series current is constant. The same current is flowing through M1 and M2. Okay, that is ID1, and the VI is nothing but VGS. Therefore, ID1 divided by VGS1. When Vout is constant, then VDS2 plus VDS1. This is constant, this is constant, let us say. Then what is this basically? This is nothing but GM1. Right? Simple. This is another transconductance of MOSFET 1. For a change in VGS, what is the change in the current of your MOSFET 1 when output voltage is constant or VDS is constant? That is what is your GM1. Simple, straightforward. Right? Problem is over. But remember, it has very advanced. This is nothing but cascode amplifier. This is cascode, not cascade. Okay? We didn't see this, right? This is what is cascode amplifier. What do you mean by cascode? Two different configurations. Basically, this is what is having common source and common gate combination. Cascode means common source and common gate. How? Applying input voltage with respect to gate, right? Therefore, if you ask me the terminals, this is gate, drain, source. Now this is gate, both are NMOSes, right? Drain, source. If you take like this, right? Now if I separate it, something like this, now you see here, we are applying the input voltage at gate with respect to source. Let us say this is output of first transistor. Taking output voltage at drain with respect to source. This is common source configuration. Whatever output you got, that is what we are applying to transistor M2. When I say applying to transistor M2, we are applying at source with respect to what? Now for AC analysis, the V bias will be connected to ground because this is DC voltage. For AC analysis, all DC quantities will be connected to ground. Therefore, gate is at AC ground. Applying input voltage at source with respect to ground. Taking output voltage at a drain with respect to ground. For both input and output, gate is common. Therefore, output of common source amplifier is given to input to common gate amplifier. Therefore, it is common source, common gate combination. You will get huge voltage gain. You will get huge voltage gain. This is what is called cascode amplifier. Okay. With this, I can say I'll stop the classroom workbook problems. Now we can see the student workbook problems, okay, in the later sessions. Take it. I think 2 more minutes. After that, the session will be over. Then we'll continue in the next session to see the student workbook problems. Okay. Answer is, what is the answer? Answer is C. Simply GM1 nearly equal to GM of M1. Ultimately, we should define any circuit or any system is defined with input and output, right? Therefore, define with input and then define with output. Whatever you have in between doesn't matter. Ultimately, what will be change in output current because of change in input voltage? When output voltage is constant, that is what is GM. That is what is coming to what? Therefore, the overall circuit GM is nothing but the GM1 of your M1. This is what is cascade amplifier. Okay. This is what is intermediate output from stage 1, that itself is input to the stage 2, which is common gate amplifier. Cascade means same stage to same stage. Common source to common source or common gate to common gate. These are all called cascade. But cascade is nothing but different configurations. Okay. Thank you.